As we have seen before, for a control volume that is at steady state, the conservation of energy principle implies that the total energy that is flowing into the control volume must be equal to the total energy that is flowing out of the control volume. Click on the shown link if you'd like to review that section. In addition to being at steady state, we assume no work or heat are being added to the control volume, and we assume constant density and uniform velocity and pressure at all inlets and outlets. We can then write the conservation of energy equation in terms of only the flow energies into and out of the control volume. Thus the summation of all flow energy going into the control volume must be equal to the summation of all flow energy going out of the control volume. Substituting the equation we got before for the flow energy, capital E dot, is equal to m dot times lowercase e. We get the shown equation that states that the summation of the mass flow rate times the energy per unit mass at all inlets is equal to the summation of the mass flow rate times the energy per unit mass at all outlets. Click on the shown link if you'd like to review that section on flow energy. We can also substitute the expression we obtained for the energy per unit mass. See that section on energy per unit mass for more information. And thus we obtain the shown expression for the conservation of energy equation for multiple inlets and multiple outlets. We have previously obtained the energy conservation equation for a control volume that is at steady state with multiple inlets and outlets. By assuming a single inlet and a single outlet, we can drop the summation sign from the previous equation. Furthermore, based on the conservation of mass principle, at steady state, the mass flowing into the control volume must be equal to the mass flowing out of it, and hence the mass flow rate can be cancelled out from both sides of the equation. We finally get the shown equation that states that for a control volume at steady state with a single inlet and a single outlet, the pressure divided by the density plus half the velocity squared plus the gravitational acceleration times the height above a given arbitrary reference plane for the inlet must be equal to the same quantity for the outlet. We then get an expression that is known as Bernoulli's equation that states that for uniform steady-state pipe flow, with no flow losses or work added, P divided by ρ plus half V squared plus G times H is equal to a constant value everywhere in that pipe. The Venturi flow meter is a device that is used to measure the velocity of a fluid that is flowing through a pipe. It is made up of a pipe section that has a constriction in the middle, that is also known as the throat of the Venturi. The pressure at the throat and the pressure upstream, or before the throat, are measured by means of pressure transducers. Or, if the pressures are not very large, the pressures can be obtained by simply measuring the height of two fluid columns at these two locations. Knowing the pressure difference between the throat of the Venturi and a point just upstream of the Venturi's throat, and the cross-sectional areas at the throat and upstream of the throat, allows the calculation of the fluid velocity within the pipe upstream of the Venturi flow meter, as we will demonstrate subsequently. We set location 1 to be upstream of the throat, and location 2 to be at the throat of the Venturi. We can then write Bernoulli's equation between points 1 and 2. Noting that points 1 and 2 are both at the same height, we can cancel out the potential energy terms from Bernoulli's equation, and end up with the simplified equation number 2. Using the continuity equation between points 1 and 2, we get that the velocity at point 2 is equal to the cross-sectional area of the pipe at point 1, divided by the cross-sectional area of the pipe at point 2, times the velocity at point 1. We then substitute the expression for V2 from the continuity equation into our simplified Bernoulli's equation, and get the shown equation number 4. We can then rearrange the terms of equation 4 to put the kinetic energy terms on one side of the equal sign, and the pressure energy terms on the other side. We can then use the pressure versus depth equation to replace the pressure difference between points 1 and 2, divided by the fluid density, with the gravitational acceleration, times the height difference between the fluid in column 1 and the fluid in column 2. Combining equations 5 and 6, we get equation number 7. Then based on equations 5 and 7, if the velocity at point 1 is set to 0, or in other words, if the fluid stops flowing through the pipe, the pressure difference between 1 and 2 goes to 0. And consequently the height difference between the columns at 1 and 2 also goes to 0. On the other hand, as V1 increases, the pressure difference between 1 and 2 increases, and consequently the height difference between the columns at 1 and 2 also increases. We can finally solve the equation for the velocity at point 1, and obtain equation 8. V1 is equal to the square root of 2 times P1 minus P2 over rho times the quantity A1 over A2 squared minus 1. And this is equal to the square root of 2 times G times delta H over the quantity A1 over A2 squared minus 1. There are several other applications of the Venturi tube, in addition to measuring the velocity of a fluid through a pipe. These include perfume atomizers and automotive carburetors. In a perfume atomizer that uses a flexible rubber bellow, a Venturi tube is used to draw out perfume from the perfume bottle and deliver it as mist from the bottle's nozzle. To accomplish this, air is blown through the bellow into a Venturi tube that is connected at its throat to the perfume in the bottle by a narrow straw. As the air stream enters the Venturi's throat, the smaller pressure at the throat due to the air's velocity pulls the liquid perfume up through the straw. When the liquid reaches the Venturi's throat, it mixes with the air, and exits through the bottle's nozzle as high-speed perfume mist. The same principle is used to mix gasoline with air in a car's carburetor. As air travels through the Venturi section that is within the carburetor, the low pressure at the Venturi's throat pulls liquid fuel into the air stream. The fuel mixes with the air, and flows to the engine's combustion chamber, where it is burned to provide power. Opening the throttle valve increases the flow of air to the engine, which in turn causes a lower pressure at the Venturi's throat, and increases the rate at which fuel is pulled into the air stream. Proper design of the carburetor's geometry ensures that for a wide range of airflow rates, the carburetor pulls the right amount of fuel, and mixes it with the air near the ideal air-to-fuel ratio for the most efficient combustion. Of course, nowadays, modern gasoline cars do not use a carburetor to mix the fuel with the combustion air. Rather, they use fuel injectors that are located directly in the intake port of each engine cylinder. This allows better control over the air-fuel ratio over a wide range of engine speeds, and during fast changes in the engine's speed. Torricelli's law states that the speed of a fluid that is exiting a container through a sharp-edged hole at its bottom is the same as the speed that a body would acquire if it free falls from the surface of the fluid in the container to the level of the hole. Hence, according to Torricelli's law, The speed of the fluid exiting the short pipe, which we call Vf, is equal to the speed of the shown weight, which we call Vw, after it falls from a height h, where h is equal to the height of the surface of the fluid above the short pipe from which the fluid is exiting the tank. Torricelli's law deals with the conversion of energy from potential energy into kinetic energy. Potential energy in the form of the object's or fluid's position above the hole in the container, is converted into kinetic energy in the form of the velocity of the object or fluid. Hence Torricelli's law is a special case of Bernoulli's equation, without the pressure term. Now let's prove Torricelli's law, that Vf is equal to Vw. First we will find the kinetic and potential energies for the free-falling object and the fluid. At two locations. Location 2 is at the reference plane, located at the center line of the pipe, at the bottom of the tank. Location 1 is at the surface of the tank, where the object initially is at rest. At location 1. For the free-falling object, the kinetic energy is equal to 0, because the object is at rest. And its potential energy is equal to the mass of the object m, times g, times h, where h is the height above the reference plane. For the fluid at location 1, the kinetic energy per unit mass is equal to 0, because the fluid that is at the surface of the tank is nearly stationary. The potential energy per unit mass is equal to g times h. At location 2, as the free-falling object passes the reference plane, its kinetic energy is equal to half times its mass m, times its velocity Vw squared, and its potential energy is 0. For the fluid at location 2, the kinetic energy per unit mass is equal to half the velocity of the fluid Vf squared. The potential energy per unit mass of the fluid with respect to our reference plane is equal to 0, since location 2 is at the reference plane. For the free-falling object, we can apply the conservation of energy principle. That states that the summation of the kinetic and potential energy of the object is constant. Hence the total energy at the initial object position is equal to the total energy at the final object position, or 0, plus m times g times h, is equal to half times m, times the speed of the object squared, plus 0. Hence the speed of the object as it passes the reference plane, or Vw, is equal to the square root of 2 times g times the initial height of the object above the reference plane. We can apply Bernoulli's equation to the fluid between locations 1 and 2, while neglecting the pressure terms, since the pressure is atmospheric at both locations. Thus the total energy at the initial object position is equal to the total energy at the final object position. We get that 0 plus g times h is equal to half the speed of the fluid exiting the tank squared, plus 0. Hence the speed of the fluid exiting the tank, or Vf, is equal to the square root of 2 times g times the height of the fluid above the outlet pipe. From these two equations, we can conclude that the speed of a fluid that is exiting a container through a sharp-edged hole at its bottom is the same as the speed that a body would acquire if it free falls from the surface of the fluid in the container to the level of the hole. We have hence just proven Torricelli's law. Note that the shown equation for the velocity of the fluid that is exiting an open container does not depend on the density of the fluid. Hence Torricelli's equation predicts that if our assumptions are true, the outflow speed of any fluid from an open tank is the same for the same height of fluid within the tank. Furthermore, we note that we could have calculated the final velocity of the free-falling object in another way, using one of the well-known equations of motion, where the final velocity of the object squared is equal to the initial velocity of the object squared, plus 2 times the acceleration g, times the distance traveled h. By setting the initial object velocity to 0, we get that Vw squared is equal to 2gh, which implies that Vw is equal to the square root of 2gh, which is the same equation we got in the previous slide, using the conservation of energy principle.